This video is about trigonometric integrals, and this part of the series is about powers of secant and tangent. So in this video we're looking at integrals involving secant to some power of k times x times tangent to some power of k times x. With the sine and cosine integrals that we just saw in the last video, there were really only three cases. If the power of sine was odd and positive, you made one substitution. If the power of cosine was odd and positive, you made a different one. And if both powers of sine and cosine were even and non-negative, then we handled it using power-reducing formulas. Secant and tangent are a little different, just because the derivative of tangent is secant squared of the same angle times the derivative of the inside by the chain rule. And the derivative of secant is secant times tangent. So we don't just have three cases here. Our textbook lists 5 cases. I'm just going to go through a few examples, pretty much one from each case. And rather than listing all the guidelines in advance, I'm going to list the guidelines as appropriate to the problem in front of us. So here's an example. Let's say you have the integral of secant to the fourth of, let's say, 5x times tangent of 5x, let's say, quantity squared dx. All right. Now remember, the derivative of tangent is secant squared. So when the power of secant is even, we can use this guideline. We'll save a secant squared factor for du. And let u equal the tangent factor. So if you've got a tangent of 5x, it's going to be tangent of 5x. In general, it's going to be tangent of kx. Then we're going to do a u sub, so we'll have to write everything that's left entirely in terms of our u, which is tangent of x, or tangent of kx. So we're letting u equal tangent of whatever our angle is. In this case, it's tangent of 5x. In general, it would be tangent of kx. And then we compute the derivative. Now remember, the derivative of tangent is secant squared. The angle stays exactly the same. And then we multiply by the derivative of the inside by the chain rule. So we're going to get a 5 there. And that secant squared of 5x dx, I want to save that for my du. The 5 I really don't need, so I'm going to divide both sides by 5, or multiply by 1/5, same thing. So 1/5 of du is 1/5 of this. So the 5's are going to reduce, and we'll have secant squared of 5x dx. And this integral can be rewritten with this secant squared off to the right-hand side. And we're going to write everything eventually entirely in terms of tangent of 5x. So after I factor out the secant squared for my du, I've got secant to the fourth here, so I'm going to have 2 secants left. Angle stays the same, and the tangent squared of 5x is still there. Now, by design, this is secant squared of 5x dx is 1/5 du. And we want to write everything that's left over here entirely in terms of u, and u is tangent. And we chose u to be tangent because the power of secant was even. I guess we should probably say that it's even and positive. Because we need the secant squared in the numerator, right? All right. So I need to write everything that's left, everything in these brackets, entirely in terms of tangent of 5x. That is tangent of 5x quantity squared. That's just going to be u squared. And the secant squared, we're going to be able to write in terms of tangent because of one of our Pythagorean identities. Now, the Pythagorean identity that comes up over and over again in problems involving powers of secant and tangent is this one. Remember, if we take sine squared plus cosine squared equals 1, make sure those angles are exactly the same. I use A for angle. Can be anything, just has to be the same. If I take this and I divide it by cosine squared, sine squared over cosine squared, plus cosine squared over cosine squared equals 1 over cosine squared. And that reduces to, or simplifies to, tangent squared plus 1 equals secant squared. So I'm able to take my first Pythagorean identity and manipulate it a little bit to get the second one. Now, according to this, anytime I have a secant squared, I can replace it by tangent squared plus 1. So this is tangent squared plus 1. And in terms of u, if u is tangent, that's just u squared plus 1. Don't forget your parentheses. This u squared multiplies to the entire quantity u squared plus 1. So now it looks like I'm ready to write everything in terms of u. This piece is u squared plus 1. That piece is u squared. That's a 1/5 du. I'm going to bring the 1/5 out front. Write my du on the right-hand side. Okay, now we're ready to antidifferentiate. This is very similar to what we did with powers of sine and cosine. Now at this point, make sure you remember you can't just antidifferentiate this piece and multiply them. The antiderivatives don't work that way. We need to rewrite this somehow so that one of our rules will apply. I don't have a product rule, not one that looks like this, unless it's a u sub, and a u sub doesn't work. But if I distribute the u squared through, then I can just use the power rule for whatever is left over. So I have 1/5 of the integral, u squared times u squared. Remember, we add the exponents. That's going to give us a u to the 4th. Then we add u squared times 1, which is just u squared. And now it's very simple. It's just a power rule. So you will bring the 1/5 down, then add 1 to the exponent, and then divide by the new exponent. Dividing by 5 is the same as multiplying by 1/5. Over here we add 1 to the exponent and divide by the new exponent. Dividing by 3 is the same as multiplying by 1/3. Don't forget your plus c, and you can distribute that 1/5 if you like. I want to. This is going to be 1 over 25, and that's u to the 5th. Now remember, you have to back substitute to finish this. In this case, our u was tangent of 5x, so I'm going to put that in here. And then over here, I've got 1/5 times 1/3 is 1/15, and that's tangent of 5x quantity cubed. So I'm going to write my tangent of 5x. When we cube trig functions, we write the power on the name of the trig function to avoid ambiguity. And then, of course, don't forget your plus c. So that's our answer. And if we go back up here, this is our guideline. When the power of secant is even and positive, we're going to save a secant squared factor for du and let u equal tangent of kx. And then after you've saved that secant squared factor for du, whatever's left over here needs to be written entirely in terms of tangent. So I had a tangent squared, and this secant squared that's left, you're going to have an even power of secant left. it can always be rewritten in terms of tangent using this Pythagorean identity. So this Pythagorean identity is going to come in handy a lot as we're solving these problems. And the reason this rule works the way it does is because if the power of secant is even and positive, if I take away a secant squared, the power of secant that's left is also even and positive, and so I'll be able to use this sometimes repeatedly in order to write the secant squared factors that are remaining entirely in terms of u. And so keep that in mind. The power of secant is even and positive. You're going to do this. All right, here's another example. Let's say we've got the integral of tangent cubed of x over 4, all divided by secant to the 4th of x over 4. And we're anti-differentiating with respect to x. Now in this one, notice the power of secant is even, but it's negative. That's a secant to the negative 4, if we bring that up to the numerator. And the power of tangent is odd. It turns out if the power of tangent is odd and positive, got another guideline. In that case, we can save a secant factor and a tangent factor for du and let u equal secant of kx. In this case, we've got secant of x over 4. So you're going to leave the angle alone. It's always going to be a constant times x. Or for most of these problems, unless we have to do a u sub first. So we're going to have u equals secant of x over 4. And then we compute the derivative of secant. The derivative of secant is secant times tangent. Remember, your angle stays exactly the same, so I'm going to substitute in x over 4 for both of these. And then we multiply by the derivative of the inside by the chain rule. You do not have to use the quotient rule to take the derivative of this. That's just a constant times x. That's an implied 1/4 times x. So the derivative of 1/4 times x is just 1/4. Don't forget to multiply by dx, otherwise it's not the differential of u. Okay, so we're here. Now there's no extra factor of 1/4 out here, so I'm going to multiply both sides of this equation by 4 so that those reduce. Turns out 4 du is going to be secant of our angle times tangent of our angle dx. Okay, so we're going to save a secant times tangent for du. And we want to write what remains entirely in terms of secant. So initially I'm just going to factor out the secant times tangent. And then I have to think about what's left. I had a tangent cubed. If I take out one tangent, I'm going to be left with a tangent squared. So that's easy. What about the power of secant? I had a 1 over secant to the 4th, or secant to the negative 4th. I need a secant here. And I need to raise it to some power. So that this power or secant to this power times secant to the first power is secant to the negative fourth power. Because remember, that's a secant to the negative fourth if it's a secant to the fourth in the denominator. So I need, remember our exponent properties, if this times this is secant to the negative fourth, this exponent plus this exponent has to be negative 4. So I'm asking myself, what plus 1 equals negative 4? Oops. And we know if we subtract 1 from both sides, the number that would go right there is negative 5. That's our box, or I don't want to use x, I'm using my x for something else. Negative 5 plus 1 is going to equal negative 4. So that goes right there. Okay, and by design, this is 4 du. It's always just a constant times du. And then everything else over here needs to be written entirely in terms of secant. Now that is secant to the negative fifth, so no problem, that's a u to the negative fifth. And then I've got a tangent squared. Now tangent squared can be written in terms of u because of that Pythagorean identity that we looked at last time. We've got that identity. 1 plus tangent squared of an angle is secant squared of the same angle. So I can use this to write tangent squared in terms of secant squared or secant squared in terms of tangent squared. If I want to get tangent squared by itself, I have to subtract 1 from both sides. And I get that. So this is tangent squared, and it's secant squared minus 1. According to our identity, the angle stays the same. And if secant is our u, that's just u squared minus 1. Alright, so I've got u to the negative fifth times u squared minus 1 and the 4 du over there. So I think we're ready to write this entirely in terms of u. I'm going to bring my 4 out front. Again, it's just a power rule, but I can't antidifferentiate this piece and this piece separately. I've got to distribute first so that our power rule applies to each term. When we distribute, remember you add the exponents. That's u to the negative third, and then u to the negative 5 times negative 1 is negative u to the negative 5. Okay, so bring the 4 down, then we add 1 to the exponent and divide by the new exponent. Dividing by negative 2 is multiplying by negative 1/2. Then the negative comes over here. You just bring that down. Add 1 to the exponent and then divide by the new exponent. Don't forget your plus c. Alright, so we've got 4 times negative 1/2. And that u squared can be written, or that u to the negative 2 can be written as a u squared in the denominator. And this is a negative 4, so that's positive 1/4. And this is a u to the 4th also in the denominator. If I have that u to the negative power, I can bring it to the denominator instead and make the power positive. If we distribute the 4, we get 4 times the negative 1/2 is going to be negative 2. And then 4 times the 1/4, the 4's are going to reduce. It's going to be 1 over u to the 4th plus c. And then the last thing we do is back substitute. And I think this one can actually be simplified further. So I've got a secant squared of x over 4 in this denominator, and a secant to the 4th of x over 4 in this denominator. Now we could stop here and this would be fine for a test or a quiz, but there is an identity, another identity, and you don't have to use it, but I think it's helpful because we've got secant squared in the denominator. Do you remember that secant of an angle is just 1 over cosine of that angle? Well, I could flip those. I could multiply by cosine and then divide by secant, and I'd get cosine of the angle is 1 over secant. Same thing. So this secant squared that's in the denominator can be brought up to the numerator. 1 over secant squared is actually cosine squared. And 1 over secant to the fourth is actually cosine to the fourth. So this is my final answer. But maybe a cleaner final answer might be -2 times cosine squared of x over 4 plus cosine to the fourth of x over 4 plus c. Those are equivalent. And we're good to go. That's our final answer. All right. Now, the fact that it can be written entirely in terms of cosine tells me that I could have started this problem and used a different guideline. Instead of writing everything in terms of secant and then antidifferentiating, I could have written tangent in terms of sine and cosine, called it sine over cosine, and then I could have written secant in terms of cosine, called it 1 over cosine, and then substituted and simplified, and I would have ended up with a power of secant or a power of sine and cosine problem, like we did in the last video. But this guideline will work anytime the power of tangent is odd and positive. Now there are going to be some cases where more than one guideline will work. That just means you're going to get equivalent forms of the same answer. So this is what we do, and this is the identity that we use while we solve the problem. All right, so if the power of tangent is odd and positive, let u equal secant. And if the power of secant is even and positive, let u equal tangent.